Okay, the people that I don't see are Amanda, Chad, Lindsay, Austin, Sally, Jaron. There's James. Okay, so that's it. Okay, first announcement. Haley, we had some miscommunication. Apparently Haley's been doing a little tutoring already before I understood things to be set up. But Haley is willing to do some peer tutoring. Obviously she's in the class. If you would like to have some time with Haley for her to help you with your physics, her phone number is right there. She prefers apparently to be texted rather than to receive phone calls to set up an appointment. She doesn't have a lot of time. Hopefully more than one person can, meet with her to, optimize the amount of people who can receive tutoring from her at her times. And, I've told her to, if there's multiple people asking, to make sure she tries to balance the load, not just have one person dominate her time. So if you are interested, there's the contact info. Okay, talking about laminar and turbulent flow. And as you can see, I have a Bunsen burner burning right here. Well, I don't know. Do we call this a Bunsen burner? It's not the traditional shape. If I lift this up, you can see here on the screen the fluid flow. And you see here a fairly smooth fluid flow, but it quickly becomes very crazy and disorganized. The nice smooth flow is termed a laminar flow. So down here, we have laminar flow. Laminar means in layers. So, I'm trying to keep my... So we have smooth layers of flow down at the bottom. But when it gets higher, it's breaking up, and you see things that are curling here. And so those are called eddies, and it's forming what we call a turbulent flow. So there's a difference there between the turbulent flow and the laminar flow. Laminar flow is layers flowing. Turbulent flow, they're not flowing. Of course, a big question would be, what's the difference in why we have one and then the other? What do you suppose is different about the smoke down here at the bottom where it's laminar flow compared to up here at the top where it's turbulent flow? What's happening to the smoke as it rises? Or the hot air. Obviously what we're seeing here is mostly just hot air, not visible smoke. What's happening to it? It's actually doing the other. It's speeding up. In fact, if you look at this, you can see here an outline that comes together up like that. It's doing that because the air is made hot by the combustion. You guys have studied redox reactions. You have the fuel, the oxidizer, and a heat source. It undergoes that redox reaction and releases a lot of extra energy, making it hotter. What does hotter mean in terms of the molecules? They're moving faster. So the molecules are moving faster. Molecules are just bouncing off of each other. If they're moving faster, that means they're going to hit each other harder. Right? If I just walk slowly into the table, no big deal. But if I walk fast to the table, it's going to hurt. I'm not going to do that. When they hit each other fast, they bounce off harder, and they push other molecules away because of these hard collisions. Much like when I was in graduate school, my roommate, who was a football player, and I would go to clubs, and everybody's dancing, and every now and then you have some people who are slamming into these poor innocent young ladies. And so then we would go out and we would come in a little bit faster and a little bit harder and knock those guys off that were hitting the ladies. Right? We felt that we were doing a good job. And it was an example of what's going on with the thermodynamics. Things get hotter. The collisions are more energetic. It causes things to spread out. If they spread out, you have less mass in the same volume. What do we call that mass per volume? The density. So the density is lower. Lower density floats up. And so we have heated air has lower density, and so it's floating up. And it floats up faster and faster simply because it has an acceleration, because it has a net upward force due to buoyancy. And so it's going faster as it goes up, and it gets fast enough where it transitions from a laminar flow to a turbulent flow. Now, let's look a little more at this. Here we see an example of a stream with laminar flow. Now note, with laminar flow, the water is not traveling the same speed everywhere. And we treat it as if it's layers, with this layer going this speed, this layer going faster because that's a longer arrow, and so on. So the water at the top is going the fastest. Why would the water at the bottom of the stream be going slower than the water at the top? Somebody say? Friction. There is what we call friction. The water can't just smoothly slide over the bottom of the stream. There's going to be some friction between the water and the stream. And furthermore, there's some friction between water flowing past other water. It's not perfectly free. And so we have something that we use to talk about that friction. That's called the viscosity. So viscosity, I'll have the word viscosity on the next slide and some definitions of it. But the viscosity is a measurement of how much that friction is between the flowing layers of water. And of course, this layer and this layer have a difference of that long. This layer and this layer, difference like that. They should be fairly similar in length, the differences in each one. This picture doesn't show them the same length for the differences, but they should be fairly smooth in how the velocity increases. Here the stream comes along and it hits an obstruction. Now what's going to happen to the flow rate when you hit that obstruction? You have a big stream, now you have less area for the water to go through. So what has to happen to the speed of the water? It has to increase. And so as a result of that increase, you have bigger differences in the speeds in the layers. And when the speed differences get too big, then that friction causes it to not smoothly flow, but to start having these curls or eddies. And so you have this turbulence that occurs because of the higher speed of flow that was caused by this. Now, it's not just the higher speed. You have directions like, water has to come up like this, so it has to change direction and go into other water. That also contributes to the turbulence. In this case here, we didn't have any obstructions. It was just the higher speeds. So the picture with we got a clicker question, then the picture with viscosity. What does laminar flow mean? So this is just the word laminar. Yeah, everyone, well, is Jaron here? No, okay, yeah, everyone's here to answer that. You had a question?
Yeah, when we're talking about the layers of the water, what is the real world application? Like, is this like particle sheet thin layers, or what is a layer of water?
Okay, let me go through this and then continue with that idea. The word laminar itself means layers. The reason uniform flow is not a correct answer is uniform flow would mean all the same velocity. That may not be what you thought when you chose that answer, but uniform flow would be all the same velocity. We do have a name for uniform flow, that is superlaminar. Superlaminar flow, you have all of the layers at the same speed. So it's uniform. Now, the question that Chad asked was, let's go real world with this. So we have water flowing. What are the layers? Like, let's say we have a fire hose. What are the layers? Well, essentially, you're going to have cylindrical layers. The thickness of those layers is as calculus would teach us, of infinitesimal width. So you have an infinite number of layers going from the outside of the circle to the inside, all in cylinders. Of course, without calculus, you have to draw them like that previous picture. We say, okay, so here's this layer going like this. Here's this layer going like this. But in reality, it's essentially this molecule with this molecule on top. And so those molecules are going past each other, and there are certain intermolecular forces. And if the speed difference is too great, the intermolecular forces will cause it to tumble, where if the speed is smaller, it'll allow it to go. Question?
Might be a little off topic. Would you then be able to have an equation that defines velocity per depth or something? How do you integrate that?
Okay. Well, you start with this.
Okay.
The definition of viscosity. Now, fluids cannot have, a static fluid can't have a shear stress. That is, remember, shear stress would be the idea if I glue my hand to the tabletop and then try to slide it horizontal on the table. The surface of the table points outward, so up. The force of my hand would be perpendicular to that. That's a shear. In a liquid, that is illustrated here, where we have a shear force created by a force that is going parallel to the lamina, the layers. It can't support a shear stress, but you do have in flow this shear flow. And so the definition of viscosity is a measurement to tell us about the relationship between the shear stress. What is stress? Blank over blank. Force over area. So this divided by this, that is the shear. We don't want to call it a shear stress per se because you can't support a shear stress. But it's still a shear that is occurring. And then you have length over V. Well, the strain is equal to delta X over L, where delta X is the distance it moves horizontally. So the delta X is perpendicular to the length for a shear stress. Now, V over L, if you multiplied V by delta T, that would be the distance it moves. And so this actually, V over L, is equal to the shear divided by delta T. So this viscosity is very similar to like an elastic modulus, but instead of having an actual shear, you have a rate of shear involved. So all of this said, what does the viscosity tell you in practice? In practice, if you have a higher viscosity, you're going to have a bigger force necessary to get the same velocity difference, which means that it's harder to make it flow. So things with high viscosity don't flow very well. Things with low viscosity flow very well. So just based on things you've seen around you, what has a higher viscosity, air or water? Which flows easier? Air. How can I test this? I can go like this with my hand in air and try to do the same thing in water. In which case do I feel more resistance? In water. Hence, water must have a higher viscosity. What has a higher viscosity than water? Syrup, okay? If I try to go through syrup now, of course, this is not the syrup that is boiling, because then it's really low viscosity. But the nice syrup that I go to IHOP and pour on my pancakes, I actually can't do that. My wife wouldn't allow me because it's too unhealthy, apparently. But that stuff would be much more resistance to my hand. So that's what viscosity means. If it has a higher viscosity, it takes more force to make it slide. And if you get a higher speed, there's going to be more forces involved and hence more likely to cause that turbulence. So more viscous materials are more likely to have turbulent flow for the same speed. So here is what the flow rate looks like. Remember, these lines now are representing velocity. So here, velocities are all the same if the viscosity is 0. If viscosity is 0, there is no hindrance for having two layers flow past each other. And so you push that water, the layer next to the wall just moves right against the water that's touching the wall with no hindrance, so you have constant speed. That's really cool if you want to make a fountain. If you want to make a fountain, you want the water to all flow at the same speed, so when it comes out, it all just continues flowing together. If it's at different speeds, think about if you are throwing a baseball. You throw at the same angle. If you throw at a faster speed, what happens? Faster speed is going to, will it go farther or shorter? Very simple question. I just want people to actually voice the answer. If I throw it faster, it's going to go farther. So if I throw it faster, starting with the same speed, it's going to be going like this, so it separates. But if I have this non-viscous situation or a superlaminar flow, you can create a superlaminar flow even if you have viscosity, then it will stick together. So if you're trying to make a fountain, you want that superlaminar flow. Or if you're trying to toss water 100 yards into a window in a burning building, you want the water to stay together, not to separate. With fire nozzles, they make them so you can have it all the same speed or very different. So how do you get that superlaminar flow? A normal laminar flow would look like this. So how do I get like this? In a fire hose, they just put a grid like that. It's about 1 centimeter long. That is, if you were looking at the sideways view of this, it's about 1 centimeter long, and it's a grid. And then it forces the water to go through each of those grids separately. And so each of those grids has something like this for the velocities of the water going through the grid. But since they all have that same shape, when you combine them all back together, you have your high speed here, and your high speed here, and your high speed here, and your high speed here. And the viscosity actually makes it so they even out, and it gives you a very uniform speed, and hence the water stays together. Now, if you're designing a fountain, you're more likely to take like straws and just put a big pack of straws together in a bundle, force the water through those straws, and it's going to come out the same speed from each straw and give you a superlaminar flow. Okay. Moving on, because I want to spend most of my time on thermodynamics, not on flow. I think this is my last thing on flow. Well, no, because I have Reynolds numbers as well. Viscous loss. In our Flip Friday, we said assuming that there is no pressure loss in a fire hose, which then I noted is a horribly bad approximation. Nowhere close to correct. Because you have viscosity. Because there is a friction between the water flowing against the walls of the hose and the water flowing against other water. So this equation here, Poiseuille's equation, I think is how we pronounce it, relates the pressure loss to the flow rate and this R that's the resistance. Here's what the resistance is. Now notice the resistance 8 times. Does anybody know what the name of this character is? Because I did not name it. This character here for viscosity. Eta. You might have seen things like or you also might see it as oops. Well, I'll just do it different. Yeah, I'll do it like that. I ate a pie or I ate some pie. We scientists or mathematician types think we're incredibly hilarious with these things. So that's eta. Eta is the symbol we use for viscosity. If you're trying to type it on your keyboard, like with the symbol font, you use the symbol or use the H button for it, just in case you're curious. L is the length of my pipe. Pi, of course, is pi. R is the radius of my pipe, assuming it's a cylindrical pipe. So, of course, pi r squared is equal to the area. So this on bottom is actual area squared divided by pi. Why is this important? Well, things like, 15 years or so ago, my father had a coronary bypass surgery. Why? Because he had a 90% occlusion in some coronary arteries. And so we can use this equation to figure out, and let me change this so you can actually answer as well, to figure out how much flow did he have through these coronary arteries. If it was 90% blocked, that means the area was only 10% of what it had been if it's 90% blocked. How much blood flow did he have going through that artery compared to the normal blood flow, assuming the pressure is the same on both sides? And notice I've written the equation here so you can think it through with the equation there. Wrote it even in terms of the area. Okay, we had 3, 2, 7, 5. Now normally I'd have you discuss this because this would be a great time to discuss, but given that I'm going to have a hard time finishing what I have laid out for me today, notice the flow rate is proportional to area squared. So Q2 over Q1 is equal to area 2 squared over area 1 squared. And if area 2 is 10%, so 0.10 of area 1, then area 2 squared over area 1 squared is going to be 0.1 squared, which is 0.01, hence 1% of the initial flow rate. That's not much blood getting through anymore. It's probably a good point to have, bypass surgery. All right. Last couple things. How do we know if the transition is going to occur and what difference does it make? This picture here, the take home from this lower picture that I would like you to get is this force. If it's a laminar flow, you have a force due to the viscosity that's drag. And that's going to follow the Stokes equation, which we learned a month ago, that the force is proportional to the speed. But if it's going faster and creating some turbulence, this force got bigger. And more turbulence is even bigger. Over here, the force is proportional to speed squared. So the drag force changes its functional behavior depending on if you have turbulence or not. So the final thing is, how do we know if we're going to have turbulence? Calculation of what's called the Reynolds number. The Reynolds number, there are two calculations. This here is for flow in a pipe, and this here is for an object moving in a fluid. So you have a still fluid with an object moving through it. The Reynolds numbers are fairly similar. In fact, the only real difference in them is the two. This one here is the radius of the pipe. This one here is the cross-sectional length of the object. Interpretation-wise, there's quite a bit of difference, though. Interpretation-wise, this Reynolds number here, you'll have a viscous flow, a laminar flow. is less than, I think it was 2,000, right? And a turbulent flow if it's more than 3,000. And in between, it's in a transition zone, it's hard to predict. For an object moving in a fluid using this equation, you have a laminar flow if n prime sub r is less than 1. And if that is larger than 10, you're going to be having it change from proportional, the drag force proportional to speed, to drag force proportional to speed squared. Your turbulence increases as the Reynolds number increases. And when you get to very large Reynolds numbers for this, you get much more turbulent flows and not just proportional to v squared anymore. It's very complicated. Notice this just has L, which is a typical length. If you have a sphere, that L is easy to determine, and this equation kind of works. If it's not a sphere, it's a little hard to determine. If it's non-uniform, you can have sharp edges, that's going to make a difference. So it's not an exact formula for anything other than a sphere as far as I know. Okay, now let's get into more thermodynamics. So we learned about temperatures. I know, we're going a little fast. We learned about temperatures in lab yesterday. And we learned about the 3 primary temperatures. So, somebody throw me out some facts about the top one.
Oldest.
The oldest. The Fahrenheit scale is the oldest. Calibration points.
Icy water and its Weiss by temperature.
Okay. Icy seawater and Weiss by temperature. Good or bad calibration points? Not very good calibration points. Hence, not a very good scale because its calibration points weren't very good. Centigrade or non-centigrade? Originally, it was defined as a centigrade scale. Today, the Fahrenheit scale is basically defined from the Celsius scale. So today, it wouldn't be a centigrade scale anymore because it's actually defined by the Celsius scale. Temperature of freezing water here, 32 degrees Fahrenheit. Temperature of boiling water, 212 degrees Fahrenheit. What's the difference between those two? 180. And we put 180 Fahrenheit degrees. Notice that was 212 degrees Fahrenheit, that's a temperature. 180 Fahrenheit degrees, that's a change in temperature. Absolute zero turns out to be minus 459.67 Fahrenheit, degrees Fahrenheit. Okay, the next one. What can you tell me about the Celsius scale? Okay, he initially had it, so 100 degrees Celsius was the freezing temperature of water, and 0 degrees Celsius was the boiling temperature. Okay, that was a 100-degree difference, so it was initially a centigrade scale. After that good Swede, Andrew Celsius, died, what did they do? They flipped it over. And then what did they do in 1977? They changed it so it's no longer a centigrade scale because it's going from 0.01, the triple point temperature of water, to 100 degrees Celsius. So it's 99.99 instead of 100. And it's absolute zero here, minus 273.15 degrees Celsius. (100 Celsius degrees), I'm not going to ask what the difference between 100 and 0 is, between freezing and boiling points of Celsius. Based on these numbers, we can make our conversion equations. You have the change in temperature is a 180 to 100 or 9 to 5 ratio. And 0 degrees Celsius is 32 degrees Fahrenheit. So that means I can do my temperature Fahrenheit is equal to 32 degrees, because if temperature is 0, I have to add 32, plus that ratio of 9/5 multiplied by the temperature Celsius. Where does 9/5 come from? Once again, 180 Fahrenheit degrees divided by 100 Celsius degrees is 9/5, and it has those degree units that I didn't write in this equation because you have shifting of units. So that's how we get our conversion factor. Very simple. Kelvin scale. What's its conversion factor? Tell us temperature Celsius, what? Just this offset, because it's the same change in temperature as Celsius scale, but it's offset, so 0 kelvins is absolute 0. So we have these 3 temperature scales that we see a lot. We see the top one because we're Americans. Now don't get me wrong, I love my country. It still makes me just a little sad though that in my country we use Fahrenheit when most of the world uses Celsius. Although you have to admit, because a Fahrenheit degree is a smaller degree, that is, you change 180 Fahrenheit degrees in the same range that would be only 100 Celsius. So a change in 1 degree Fahrenheit is a bigger, or is a smaller change. Using Fahrenheit temperatures, you have a better idea what the temperature is if you, for the same number of digits. But that's the only positive I can think of for the Fahrenheit scale. What is the scientific standard? The SI base unit. Kelvins. Kelvins are the SI unit. Now we will use Celsius and Kelvin quite a bit, but almost never will you be wrong if you use Kelvin. There are times you will be wrong if you use Celsius. If it's a change in temperature, either one works. If it's just temperature, like temperature raised to the 4th power, you'd better use the Kelvin temperature. With that in mind, which statements are true about the Celsius temperature scale? So answer the correct ones, multiple correct answers, and then hit enter. You're not in yet. Nope. You and... There we go. Okay. So we had 17 who said it was developed by a Swede. That is definitely true. What's his name? Yeah. Celsius. Good call. We had 9 people that said it's a centigrade scale. Originally that was true, but it's not true anymore, because now it's a 99.99 instead of 100 scale. Originally, 0 degrees Celsius was the temperature of boiling water. 18 people remembered that's correct. He had it flipped originally from what we have now. An absolute temperature scale? No, absolute temperature scale is 0 at absolute 0. The Celsius scale is minus 273.15 at absolute 0, so it's not an absolute temperature scale. That's the definition. The SI unit had 3 that said that. What's the SI unit for temperature? Kelvins. Okay, so the correct answers were these 2. So, thermometers. We used a thermocouple yesterday. I don't have that as one of the ones in my pictures. We used a glass bulb to measure the temperature of the water because you couldn't bring thermocouples up here and couldn't bring the water back there. So the one on the left, that's a glass bulb with, in this case, alcohol in it. We often like to use mercury, but as we talked about before, mercury is a mildly harmful substance and we're very, very afraid. It's kind of like radioactivity. We're very, very afraid. No one knows why. One of my professors in grad school, the one that's in charge of the reactor, said if I were to take all the radioactivity in your body and put it in a cube that was 1 centimeter squared, I couldn't give it to you because it'd be too radioactive for you to handle. Right? We just have this fear of radioactivity that there are reasons for fear, but not nearly as much as we have fear. This here is called a bimetallic strip. And it probably has 2 L's in metallic. I can't tell. I'm going to erase it. Maybe. The bimetallic strip is made by having 2 pieces of metal that are dissimilar. So let's see. I shall have Tori be my videographer again. Oh wait, I gotta do something first. Crud. That's not what I need to do. Cancel this. Change it from that. Then go to here. Maybe. Come on. There we go. Now, I think if I turn this off, it'll work. Nope, that wasn't it. Poo. Well, okay. I don't know how to get it out of the mode. Okay, so I won't have Tori do my videography because I apparently can't remember how to use my tablet right. Okay, chat. When you look at the 2 sides of this, how do they look? The 2 sides of the metal. One's wood.
Different.
How are they different?
One has a sheen reflection, and the other is one has a brass, like the other has a more silver.
Okay. That's not just enough. You can see that there's a difference. One has a more brassy look, one has a more silverish iron look. If I put it in the flame, what happens to things when you heat them up? They expand. If they're different materials, they're probably going to expand differently. So I put it in the flame, and it curls right up. Now, what would you tell me about the expansion of the 2 sides? It's curled into a loop. Okay, the outer one had to expand more. The outer one expanded more. They're bonded together. But as you can see in this picture, nice work. The length here is longer than the length here. It's like a circle. If they were in a perfect circle, the circumference is 2 pi r. And so the bigger r is, the bigger the circumference. And so it curls up in a circle to maintain them being bound together but having the one that's longer on the outside. And the bigger the difference in length, the tighter the circle, the tighter the circle has to become. This one here, I don't know if I've probably seen something like that. The idea is you take that bad boy and you just stick it on your forehead. And then if you are a warm enough temperature, some of those start lighting up. Now, they're really lighting up? No. What they're doing is they're becoming reflected to certain colors. They're using plastics or polymers that at a certain temperature, they will start reflecting certain colors. And each one has a little different, the temperature where it starts to reflect. And so you can just put that on there, and hey, it lit up down to here, so I'm this temperature. It's a pretty cool technology, right? It's simple. It's something that a little kid can read easily. It's easier to read than a glass bulb. And then this here, we used that in lab yesterday, except for ours were little lab versions. It's actually looking at the light emitted. Now, you look at your skin and you don't see it emitting light. You just see it reflecting light. That is, if we turned off all the lights and we were in a dark room, you wouldn't see yourself glowing. But you are giving off infrared radiation. You're giving off light, just not in the visible spectrum. And that's what this is looking at to determine temperature. Now, talking a little more about thermal expansion, here are 3 examples of thermal expansion. One of these is not like the others. Which one is not like the others? this one here. So we're going to examine this one separately from the other two. This here, that's an expansion joint on a bridge. You make a bridge. You have a homework problem. I made the homework early because the students in the gymnaires want to get started on before today's lecture. At least one of them did. Okay. So you have a problem that talks about, I think it's the Golden Gate Bridge. Gives you the length of the Golden Gate Bridge. It says, okay, so if the bridge was made at 15 degrees Celsius and it's this long, how long is the bridge going to be at 40 degrees Celsius? What's going to happen to the length of the bridge? It's going to grow. And it's going to grow. We have it there at the top, the equation to calculate how much it's going to grow. Its change in length is going to be the original length. So that's why you have to know how long the Golden Gate Bridge is. Multiplied by alpha, which is the coefficient of linear expansion. It's the number that tells you how much it's going to grow per degree Celsius change per original length. And of course, delta T is the change in temperature. What unit should you use for delta T? Celsius or Kelvin. Either one, because the change is the same. Don't use Fahrenheit. So you can calculate that difference in length. Of course, the Golden Gate Bridge, the two sides of the bridge aren't moving farther apart when it gets hotter. So what you need to do is make the bridge so it can actually change length. So they have these expansion joints. So on a hot day, you have these little things here are coming pretty close to the edge. And on a cold day, they pull apart. So the expansion is taken up in this little expansion joint. If you didn't do that, you would have one of two problems. Either you would have, on a cold day, the bridge would be in tension and you'd pull it apart at the weak spot. Or on a hot day, it'd be in compression and it would buckle. And both of these things, of course, have happened. You might have driven on roads where the road goes like this. You know, you have an asphalt road that goes like this. Probably because it got hot and the asphalt expanded. Even asphalt, which, you know, when it gets hot, it becomes kind of liquid, does that because of the expansion. And then it makes for a non-fun road. This here we actually already talked about. I just put it here as an example. Why is the water pipe not like the others? It's what? Okay, it's not a linear expansion. Water is really bizarre. I hope that I put this in the same order that I'm lecturing. I mean, there's only 4 more slides, so it's got to be close. Nope. First I put coefficients of linear expansion. When you're doing a problem, you just look up. Okay, so I have something that's made out of gold. So here's its coefficient of linear expansion. Over here I have the coefficient beta, which is a volume expansion. Now you might wonder, how are those two related? Well, let's just say I have a sphere. A sphere has a volume equal to 4/3 pi times radius cubed. Right? So if the radius is going to grow, according to my equation, delta R is equal to the initial R times alpha delta T, then I can say my R is equal to delta R plus the R initial, which comes out to be R initial times 1 plus alpha delta T. So if that's the radius, then radius cubed is equal to the initial radius cubed times, and I have to cube this 1 plus alpha delta T. Anybody learn the quick way to do that? Yeah. Wait, what's the name of that triangle?
Oh, I don't know. It's named after a guy, right?
Yeah, there's a triangle named after a guy. Ryan and I are in cahoots. Neither of us can remember. I think it's Pascal's triangle. Pascal's triangle is 1, 1, 1, and then you take the 1 has a 0 outside. You just add up the numbers above. So here it's a 0 and a 1, 1. Here it's a 1 and 1, it's a 2. Here it's a 1 and a 0, it's a 1. 1 and 2 is 3. And this tells me the coefficients to use when I square a binomial. So it's going to be 1 cubed plus 3 times 1 squared times alpha delta t plus 3 times 1 times alpha delta t squared. I know you can't read that. It actually doesn't matter. Plus alpha delta t cubed. If delta t is a small temperature, well, actually it's alpha that's small. If alpha is small, alpha squared is much smaller. And so we say that these two here are approximately 0. And we say that r cubed is approximately equal to r0 cubed times, of course, 1 cubed is 1, plus 3 alpha delta t. This here is our beta. So beta is basically 3 alpha for most materials. It just comes from geometry, things expanding in 3 dimensions. Important things to note from this table are everything here. We might have had a problem in the reading quiz. This says approximately 12. When I looked at it, I saw minus 12. And I went with that. I'll have to change that. Sorry about that. That would be vision problems, apparently. That tilde means approximately. I'm glad I noticed now rather than never. Okay, so we have variations in the expansion. Notice liquids expand a lot more than solids. And what do we make glassware out of in the laboratory? Things like Pyrex. Why Pyrex? Because it doesn't expand very much. That means we can heat it and not have it break. Why would things break when you heat it? Because if you heat something that's glass, one side heats up before the other. And so one side expands before the other. And so when you have one side expand and the other side didn't, you're going to have a stress, and that can break the glass. So if it has a smaller thermal expansion coefficient, it'll have less stress, less likely to break. And they actually, I don't think they use Pyrex as much anymore because they have glasses that are actually smaller expansions than that. Quartz would be too expensive to make it out of quartz. Okay, now it better be water. No, absolute zero. I meant to put this one way earlier. Question?
The glass blowing negative, do like use certain kind of glass?
No, they try to heat it uniformly. So they sit there and rotate it and stuff and try to get it so it's more uniform rather than just... Okay, absolute zero, the concept of absolute zero is actually kind of easy to predict. If you take a gas and you measure the pressure and volume as the temperature changes, actually this is keeping a constant volume and just measuring the pressure as temperature changes. You can do it both ways. The pressure changes in a linear fashion. Of course, when it becomes liquid, it would change, so you have to stop before you get to liquid. But if you extrapolate, these all meet at one location, which suggests, and it meets at a location of zero pressure, that suggests that there must be a minimum temperature where you would have, no matter what the gas volume is, the pressure is going to be zero. And so that led to the idea of an absolute zero temperature before there was an understanding that temperature is measuring the average kinetic energy of the particle. Okay, now we're down to the final 3 slides. One of them has to be, okay, this is going to be not water yet, but my next example, which I wanted to get done before class. Expansion of things. Now, first simple demonstration, the ball fits through the hoop. Now I'm going to heat this hoop up, and as it's heating up, I'll randomly talk. What's happening to the side, not the hoop, but the ball. What's happening to the size of the ball as I heat it up? It's increasing. So if I wait long enough, and from my pre-class experimentation, I need to wait about 15 seconds. I probably waited long enough. Okay, it just barely fits through still. Need a little more heating. Okay, so won't fit through. Cool it a little. Now it fits through, so it's very close. I'm going to heat it just a little more to make sure it doesn't get through. Okay, won't go through. What can I do to make it fit through again? I can either cool down the ball, or I can heat the ring, because the ring is going to expand just like the hole in the ring will expand just like if it was made out of the material. So if I get the ring to the same temperature as the ball, not quite there, then it just fits through again, because the hole grew as if it was made out of the same material. Now, this is always fun to do. What's going to happen when I take very hot things and stick them in nice cold water? What's it going to do to the temperature of the water? It's going to make it hotter. The parts that are touching this are going to get really hot really quick. So, I have our traditional quenching, which was the rapid boiling of the water that was just touching the very hot thing. Okay, so holes grow just like they would if you had a solid in there. Finally, the water. Water is anomalous for two reasons. Number one is water has its highest density at 4 degrees Celsius. If you cool water from 4 degrees Celsius, it becomes less dense instead of more dense. Then the next one, the really big surprise, is when water freezes, the density drops pretty significantly. From about 916 kilograms per meter cubed to about 1,000 kilograms per meter cubed. That's a pretty big drop. That's really, really important, because that means ice will float. So when it gets cold, ice forms on the top of a lake and it stays there. Ice makes a good insulator. And so you now have an insulator to keep heat from going out of the lake. So you keep a lake that's not frozen. If ice was more dense than water, what would happen when you form ice? The ice crystals would sink and you would have ice in the bottom of the lake. No insulation, what happens to the top of the lake? It freezes again, sinks again, and you would just completely freeze your lakes if ice didn't float. And so that would be bad. Okay, we're out of time. I want to ask you the clicker question. The clicker question was, what would happen if if ice sank?
So is that why igloos are good?
Igloos keep you warm because the ice is a good insulator. And so even though you have 32-degree wall, you don't have heat flowing through that wall, so the air temperature inside can be much warmer than the temperature of the wall.
How does it do? So wouldn't that melt the walls though? That's what I've always
Over time, yeah. Take a long time.